So let's start the call. We have 1 hour, and I'll give a brief intro, and then I'll get it going. It'll be mostly in technical in nature. So let me just kickstart the call. So hi everyone. My name is Vijay. I'm the founder of Vertical Serve and also a core technical member here at Vertical Serve. I've been working with Kafka for a very long time, since the early days when Kafka was open sourced. We are a partner of Confluent, Cloudera, Red Panda, and even other variants like Avian and open source Kafka. So our team has been contributing to Kafka and Kafka-centric products. Some of them are open on GitHub. If you go to GitHub/Insight Lake, you will see those products. We do like learning exercises. A lot of times we have meetups. We go over Kafka, but as a company, we are not just a Kafka company. We are a data company working with data, AI, ML, enabling a lot of enterprises on their data-driven journeys. So we cover a lot of topics like streaming, big data, cloud, then different pillars like governance, AI, ML. Gen AI is a new one which we have been helping a lot of our clients. But this call is purely around streaming and Kafka use cases. So in last 10 years, we have worked with 50 plus customers, helping their challenges. And a lot of times, we contribute back to this community where whatever learnings we had on the design patterns, we can guide customers and the wider community. So this call or this session is basically about the state store management. I'll give a very brief intro, but assumption is you guys have already have the knowledge of streaming solutions like Kafka Streams, Spark, Flink, and you know how to do those stream processing, and you have been using state store for some of your aggregation join scenarios, or even tapping into the lower level APIs of these frameworks to basically control the state store, where you are storing your key value pairs, retrieving them, and performing some of the enrichments through your state stores. And we'll also go through the Q&A section at the end of this call. Let me get it going. Okay. So very brief overview of the stream processing. In Kafka ecosystem, when you launch a KStream, you know that the KStream basically will connect to Kafka topic or list of topics, read basically data from these topic partitions as a consumers. So there is a consumer protocol underneath the streaming framework, which will connect to the topics, read partition data in an order fashion by doing the poll operation, and then take the data and pass it down to the topologies. Underneath, there are topologies at a lower level, where these topologies could be performing join, filter, aggregate functions, or if you have written your custom processors, these topologies will basically have access to the data elements coming from those topics in real time. And at processor code level, you can perform any action you want to perform. So a lot of times you do aggregates, enrichments, either by using the higher level API framework in KStream like DSL, or even the processor topologies. If these operations are implicit operations, then they have a underneath state store, which these operations utilize to store the intermediate results. Like for an example, if you are doing the aggregates across some key, for an example, if different users are going to websites and we are collecting the clickstream data, so you have user ID as a key in the topic and the the wider metadata around which user, what location, which browser type, all those information come to Kafka, right? So then based on the user ID key, if you want to do some sort of aggregation that how many unique users are coming to our website, and that calculation your KStream application is performing, then those keys are segregated to different processors in parallel, and they will perform those group by computation on some sort of a window. So you will define a window that, okay, give me every hour how many unique visitors are coming. So those windows data and their aggregation, intermediate aggregations will be stored in the state store. So that is well and good. In some cases, like you are writing your own custom state store where you want to say that, okay, I want to remove duplicates, or I only want to use unique users. So in that case, you might want to say that, okay, whatever the user ID which is coming in, the hash code which is coming in from these topics, we will probably create a key value pair, use these keys in the custom state store, and look up in a given window, like let's say in a 1-day period, I want to perform and remove those duplicate users. So you will go and take a key which is coming to the state store. You will look it up. If it's already there, you will assume that this is a duplicate, and you will not pass it down to the next hop. So in this example, you will see consumer 1 is pulling data from the topics, passing it down to the topology chain, storing some intermediate data to the state store, and then finally producing it to the final topic. And that could be your, in this example, that could be your count topic, where you are putting user ID as a key and then total number of unique visits in the topic. So a typical stream processing threads, but think about this. When you are dealing with billions of users coming through your website across the world, right? And those users or user IDs you want to store in the state store. And even the time window, let's say if you are increasing your time window from 1-day checks to a 1-week check, the amount of data in the state store will be huge. And that's where the management of memory, management of resources, and managing these state store from the recovery perspective becomes a very, very key aspect. And we'll talk about some of the challenges, how to deal with that kind of a large state store, what are the different design patterns, how to handle those larger data sets which you need to cache it for enrichment purposes, and we'll cover those aspects. So Flink is another processing framework. It is a little bit different than KStream, because KStream, you will implement the complete application will run the KStream framework in your Maven. Like you will have the KStream dependencies added, and you will invoke when your application starts, you will start the topology and all. So your KStream app itself contains the complete framework. In case of Flink, the framework is run by the Flink cluster, and Flink cluster has these job managers and task managers, which will take your code, and your code, which is basically a defined data flow, which will be submitted to the Flink cluster, and Flink cluster will run that code and perform the operations. So once your Kafka, like a Flink processing code, is submitted to the job manager, and it instantiates number of tasks based on the slots available, these tasks will then connect to the Kafka and start processing in real time those operations, applying the whole data flow graph. And for the state management, Flink also has multiple options, utilizing in-memory or RocksDB as a persistent state store. And the challenges are similar when we deal with the large state store. Any questions so far at a very, very high level? Or are we all good? All right. So
I'm good, thanks.
Yeah, go ahead, Devin. Do you have any question, or all good?
No, I said I'm good. I'm thanks. Sorry. Am I audible?
Yeah, that's fine. Okay. So let's go through the a little bit, let's double click on the state store, how it stores information. And then we will dig deeper into how can we, what are the challenges we will face in the stream processing application when the data which gets stored in the state store is huge, and how can we optimize this whole stream application to handle those scenarios. So if you see this example, if we double click that architecture and we go deeper into the state store side, our KStream pair, key and value pair, which is coming into the processors where they are these processors, whether implicit or explicit, they are operating on these tuples, right? Key value pairs. When they operate on, let's say, aggregate, where aggregate operation is, it needs to read the old value from the state store and then add new value and put the new value back in the state store, so that you will keep aggregating the new key which you are detecting. So in this case, if you see, there are simple operations happening in the state store for intermediate results. To get the old value, you will perform a get operation. Get, k is the key value. It'll go to the state store underneath, whether you are using in-memory state store, then the data is not persistent. There are two types of state store: in-memory state store, where data is not persisted to RocksDB, and you might lose the data in case of failure. In case of RocksDB state store, data is also stored in RocksDB, and RocksDB then stores in its internal data, the internal memory data to local file system. Plus, it also sends the data to the Kafka topic, the changelog topic. And this changelog topic is nothing but a k-table, which is compacted topic. The new key value overrides the old value. And the whole operation, get and put operation, is handled by the state store implementation. So we'll focus on the RocksDB because that's typically most of the companies use in production. And we'll talk more about the RocksDB and its optimization aspects. So if you see here, like old value get k operation is retrieved from the state store if that value might be there in the cache, or it might be read back from the local file system. And then the value which is coming in the stream will be added to the old value, and the new value will be put in with that key. So that new value will then update the KV pair in RocksDB in memory, which will get flushed to the disk periodically. And also whatever got changed will be sent to the Kafka topic and the changelog topic. So as I was mentioning, there are two different type of state stores in the streaming framework. Persistent state store, which uses RocksDB. It is fault tolerant because it also sends data to changelog topic. And it is suitable for most of the production scenarios. That's why we recommend everyone to use RocksDB unless the data criticality is not there. In-memory state definitely is faster. It has lesser component to manage, but you are using the JVM heap, and there are some limitations. So if your goal is to only have a smaller data sets in the state store, and even if you want to use a changelog topic, you can use it. Otherwise, there are scenarios where you might lose data. So key challenges, when we were discussing about this clickstream data and capturing, let's say, unique user across a day or a week, the main challenges are once the state store becomes huge. First of all, there are scalability challenges because now each streaming instance is carrying that much data in memory as well as the disks. So the RocksDB diagram, what we were seeing, the data basically was stored in the cache as well as the disk, right? So that large amount of data is stored on the disk. So every KStream instance now requires, or if you, let's say, deploying on the Kubernetes pods, each pod will require more RAM for the caching as well as the disk space so that you can store that. But that's not it. You have to you have to basically understand that as your number of partitions grow and the data is coming on each partition thread will have its own state store. If the topologies are complex, they will have their number of state stores handling this much data. And the recovery also becomes challenging because if the data is stored in the Kafka topic, the change block topic, there is a lot of network throughput gets utilized to send that much data to Kafka and read it back when the recovery happens, because you need to reconstruct the state store back. Until then, until your state store is backed up again, your Kafka instance, the KStream instance will not start processing the data. So that's a big challenge on the scalability side, because it does require a lot of resources, both memory, disk, and the computation aspects. From the read-write latency perspective, any get or put operations, once it becomes too large, will be a challenge, because the state store RocksDB was designed to be a more of a write performance heavy. But let's say you're trying to read the data when you were doing the get old data, right? Uh, you have to hit the cache first, and then go to the disk. And on the disk RocksDB, the data is stored in SS tables, and we'll go over the architecture of RocksDB to show that how it is a very intensive IO operations to retrieve that key data once it becomes too large. And not only that, but also the compaction and other aspect becomes huge, because data will be sent down. A lot of events will be sent down in the RocksDB. It'll get compacted, stored in the disks in a more compacted manner. There are threads working on that. So overall latency increase happens if the state store becomes huge. So how to optimize that, how to optimize read and write aspect on the state store so that our overall end-to-end latency in KStream apps are maintained and managed in a much more performant manner. So we'll dig deeper into that. We already covered the resource utilization, both from memory and disk perspective. There'll be a huge impact. So we'll cover that. Fault tolerance also, we did cover a little bit that when the application fails and it needs to restore it back through changelog topic, it'll take a long time to restore. So large state store will cause a lot more problems, and we need to look into different design patterns or different options, how to fine tune, monitor, and optimize those things. So one thing to start with, once you have, so we can tackle the challenges one by one. So the fault tolerance or restoration of large state store is one challenge. How do we solve that? So there is an option in KStream, which is called standby replicas. So what does standby replicas do? So when you launch 2 or 3 KStream applications, like instances working on the similar data set, similar topic, right? If you configure a standby replica, then will be another instance of state store created on the other instance, which is working in parallel. So let's say instance 1 and instance 2, they are working on the clickstream data topic. So instance 2 will launch another state store, which will be backing up the state store for the first instance. And how does it back it up? It reads the changelog topic of state store 1 and keep it ready. So it will always be in sync with the state store 1. So whenever a failure of instance 1 happen, immediate switch over to the instance 2 will happen. And then the instance 2 will not wait for the state store 2 to recover fully, because it's already in sync. It does not need to recover from Kafka, right? So the recovery part we can easily improve by configuring the standby replicas. So that can solve our one challenge. This also provides like a lot of benefits, but it comes with additional overheads, because now you need to make sure that your other instance which are storing the standby replicas have enough memory and disk available. to handle those scenarios. So definitely there is a resource utilization overhead. You also need to make sure when you are launching these standby replicas that you can stagger them across all instances so that these are all, they will then perform the balance utilization of your core resources. You don't want to put multiple standby replicas on only few instances. It's always a good idea to balance them around and monitor them, monitor the overall replication lag, what is happening on from the change log topics to these standby state stores. And that monitoring, you can look at some of the JMX beans, what you need to monitor, create those dashboards and keep track of those things. So standby replica, definitely, if you have a large state store, it is highly recommended to configure those for better recoverability aspect. So this is how we can configure standby replicas. So in the properties, you have a streams config, and you can just set num standby replicas config to 1. And that way, you can configure the replicas. Any questions so far around standby replicas? All right. So let's talk about caching. So we discussed about the throughput drop when we have a large state stores. One way we can improve throughput is by doing the caching. And the caching means we can use, again, in-memory cache, which is there by default in our stream apps. I think it's 10 MB or something, and you can easily configure the larger cache. And these caching layers stores the intermediate data, again, keys to the cache before it passes down to the state store. So when you have enabled these cache, by default it's enabled, you can disable it. Let's say the same aggregate scenario where we were reading the data and writing the data to state store. So when we were reading the data get k, the stream, when the cache is there, stream will first try to look for that key in the cache, and then it will go to the state store, and it will improve the read performance by going to the cache. Same thing with the write operation. Let's say if you have that same user key for user 1, the user is browsing and generating a lot of clickstream events. So if the same keys are sent multiple times in a very short period of time, when you are going to do the put operation many times, what will happen is that put operation will happen in the cache, and eventually the flush will happen from cache to the state store. So lesser data will go down and downstream, and will improve your write performance also, the throughput, overall throughput. It will definitely reduce the latency because now you are reading from cache instead of getting down to the state store, even the rocksdb file disk, reducing the IO operations. So that basically improves the overall performance. So always make sure when you have a large state store to see whether you have configured right amount of cache, which could be utilized for these. And these caching layers are used not only for your custom processors, but also your implicit aggregate. Even if you're using DSL layers, that cache is utilized for those scenarios. So it's very important to improve the throughput by having the right cache implementation. So to implement the caching, you have default is 10 MB per stream thread, and you can always change the configuration parameter in the streams cache max byte buffering, and you can increase or decrease, and you can always monitor the throughput performance by monitoring the cache hit and miss ratio JMX beans, and you can also look at the flush frequency size to set the caching parameters optimally. Again, it will definitely improve a lot of times KStream apps or the streaming apps, generally when you do complex joins or aggregations, they basically reduce your throughput. And to improve the overall performance of those streaming applications, to reduce the latency and the overall performance, look at the caching aspect. So that is the second best practice, what we should do when we need to improve the KStream application or the streaming application. So let's double click on the RocksDB side. We have now looked at caching standby replicas, two options for the improvement. Now let's go deeper into RocksDB and understand what can we fine tune there as well to improve it, right? So RocksDB basically was built by Facebook. They basically took Google's Level DB in-memory database implementation. And the whole idea was that we want to keep in-memory database. It's not a distributed database. It's a per instance database, which will have a very high throughput. So most of the time, relational databases, they have a lot of logs, controls, and the way the data gets stored in the storage engine, like for example, MySQL and all, you use InnoDB another way, it's not performant enough. So to improve the performance, you would always want to do like a kind of a wall-based mechanism, which is a write-ahead log, and then you keep on flushing it to the disk and managing those keys, implementing Bloom filters, indexes, and all to retrieve the data much faster. So that design is basically was implemented in LevelDB, which got further enhanced by Facebook, and they released RocksDB. Now RocksDB is being used by many applications or open source framework like Hadoop. You have Kafka, like KStream, Flink. They both use RocksDB. And underneath, like whenever the RocksDB stores the data, the key and value pairs, it uses the LSM tree-based design. It is highly configurable. So you can, by default, it uses the binary tree search, and you can even change the model to use hash map based search to make the performance O1. Again, the fine tuning on the RocksDB side, whatever default comes from the KStream, I highly recommend not to tweak a lot of stuff unless you are like, so you understand the RocksDB internal really, really well. Because otherwise you will have to keep monitoring, and whenever your workloads change, then you will have to fine tune them constantly. So only change few parameters which are most important, and don't change the architecture, overall architecture, how RocksDB is storing data or retrieving data, unless you are highly deep into technology as well, like how highly deep into the RocksDB understanding. So RocksDB is also implemented for very fast writes. KStream, when it uses RocksDB, KStream framework, when it uses RocksDB, basically optimizes it further. So it uses, like for an example, by default, RocksDB uses level compaction, but KStream changed it to universal compaction. And you can go and look at some of these things in much more detail at the RocksDB GitHub page. There is a wiki, and it can explain like what is level compaction, what is universal compaction. And again, there are concepts like write amplifications and the read amplification aspect. So you can see what parameters you can fine tune to optimize those things. If the disk is more important to you, which is storing the data, you can look at these compaction strategies. That will definitely reduce the disk usage. If like in Kafka, the assumption is we want performance more on the writes aspect, and disk is okay, like we can increase it, use SSDs, and we choose universal compaction there. But the options are always available to you. I will show an example how do you configure these parameters in RocksDB for your streaming applications, and you can utilize that accordingly. So understanding the read and write paths are very, very important when we are going to fine tune these layers, right? So first of all, let's go through the write scenario. We saw that aggregate example again, where we were doing the put key and the new value. So when the write request comes, RocksDB internally has a concept of mem tables. So these are active mem tables, which are again LSM tree-based artifacts, the data structure. You write your key and value, and until the buffer write whatever write buffers by default. I think 64 something MB is there. We need to double check that, but whatever the write buffer size is, your write request will happen once it reaches the buffer limit. It will basically then convert it into read-only mem tables, and a new active mem table will be created. We'll not go through the transaction log scenario. RocksDB support a transaction log where whatever you are writing into the mem table can go to the step 1B. You see step 1A, you write it to the mem table, step 1B. From there is a transaction log which keeps on appending to a log file. And then these logs are again stored in the disk in a much for more fault tolerance. That is by default RocksDB implementation. In case of KStream, we did not implement that path, step 1B path. It follows the step 2, where these read-only mem tables are periodically flushed down to the disk as SS table. And these SS table files are then later on compacted by the compaction threads. So now we understand the right path, right? All of these different steps exposes your JMX beans. You can write, you can create like dashboards to see how many requests are coming in, how much data you're getting into the mem tables. Look at the mem table sizes. You can see flush period, frequencies, and you can also see the compaction metrics, is like how many times compactions are happening, how much data is getting compacted. Same thing as part of the write operation. One of the key metrics is the write stall. So when you are writing the request, the data which is getting flushed down to the disk, because of the IO operation, if it's, let's say, lagging behind, you will get write stalls. So good metrics, JMX metrics, will give you enough indication that write performance is suffering because some of these configurations, and you can go and tweak maybe the active mem table sizes or how compactions are happening. We can dig deeper into compaction threads. Like there are a number of threads you can increase in compaction to improve the compaction performance and all. But again, there are both pros and cons when you change some of these things, because it might require more resources. So it is a read path, but I think the title is title is wrong. So let's understand the read part. When we were doing the get key and the old value we were trying to retrieve. So first thing what we do is like when that operation comes to the state store will try to read the mem table first. It'll see that if that key, because if the key is written just now in the active mem table, the data will be there. So it tries to search in the active mem table. If it's not there, then the step 2 is it'll go to read-only mem tables. If data is not there, then it'll hit the block cache. So block cache is again like you can think of as a cache which is storing the recently read data, and it'll basically improve the performance. So as I was mentioning earlier, if you have a very large state store and let's say you are trying to do the uniqueness check, if the key is already there, then when you are hitting the state store to do the get operation of that key, if data is not there in block cache, you are going to the SS tables files, and SS table files are then searched based on the Bloom filters and indexes. And it takes time because now this SS tables these are IO files, right? So any IO operation, if you are doing, it will decrease the performance. The latency will increase when you will get the get response back. So your whole topology will then have much more latency to go further down. So after you get this K, the new value will be created, written back, and then the new data will get pushed down to your next topic. That whole operation will slow down. To improve the performance, then you will have different options. Again, same thing, active mem table size. You can increase that. You can increase the block cache size. All of these increases will require more resources like memory allocation in your KStream application. So if you are defining a KStream pod, I would highly recommend, generally KStream pods should get like 8 GB, 16 GB, even up to 32 GB of memory. And RocksDB, the most important part you need to understand is the RocksDB memory is basically stored off heap, not on heap. So in KStream, your cache, when you enable the cache in last example, that is going on heap. Your producer queues, where producer buffers the messages before it goes down to the Kafka topic layer, those in-memory queues all are stored in your JVM heap. So whatever XMX parameter you are provisioning your KStream with, so that is your JVM heap size. So that if for large state store applications, you can do 6 GB, that should be good enough. But overall pod memory needs to be higher because RocksDB is going to use that off heap. RocksDB was built in C++, and that these libraries are loaded by KStream applications, and the JNI interface interacts with these. So it's important that off-heap memory is enough to support the block cache. There is a capacity planning exercises where you look at your topology and you look at how many state store it will be launching, how much memory per block cache you are allocating, and you do calculations and you come up to the right RAM requirements. So again, like you can, as I mentioned, block cache tuning, you can increase the block cache, that will improve the performance, reduce the latency. You can also bring in the Bloom filters and index in memory, which will again require more memory because Bloom filters by default are stored in the files. So when your application is trying to read data from the files, you know which file will contain the key by utilizing these things. So if you bring it to the memory, it will definitely improve the performance, but it will add more memory overhead for the read path. And again, like all of these actions expose JMX beans, and you should monitor those JMX beans to monitor the performance of overall system, and you can fine tune those things accordingly. So overall, on the RocksDB side, as I discussed, you can definitely change the memory, block cache, mem table sizes. You can bring in Bloom filters and indexes to in-memory and change that. So there is even much lower level configuration for Bloom filter, where Bloom filters are generally stored in bits, and you can increase the number of bits to have a more chances, like to have more accuracy. So there is, I will not go into the Bloom filter design, but there is even a layer of implementation where you can fine tune those number of bits to improve the true positive search scenarios to improve the performance. Parallelism is another one where you can increase the parallelism in RocksDB by increasing the number of threads in Rocks, like doing the compaction and all, so that data is always available. We can dig deeper into how compaction works by looking at, I'll just give you a brief example. So when SS table file is written first, so these are all different level files. So it's level 0 file, and level 0 files are smaller files. The compaction threads will come, will basically gather these level 0 files, store them in an ordered fashion, so that range queries can happen in a much more faster manner. And those compacted files will then merge into level 1. Level 1 files will merge into level 2. So it's a layered level scenarios, levered storage. And when you are searching something, you basically go to appropriate level to retrieve the files from the SS table and all. And there is, again, you can fine tune those things in a much more like efficient manner. I would highly recommend that focus on memory management first. If everything works fine, then you're good. Then you focus on Bloom filters. Then maybe you can increase the number of compaction threads. And then, like, if that also does not work, you can then take a look at changing the RocksDB LSM structure to more hash table manner, so that the data retrieval from mem tables, instead of binary tree search, we can use the O1 searches. You can also take a look at the level compaction versus universal compaction if the space is more bottleneck. But because these are large state stored, large number of data will be stored on the disk. Again, one more important fine-tuning exercise is that we, for the incoming partition data, because these state stores are lined up with partitions, right? So if a topic has, let's say, 10 partitions dealing with, assuming like, let's say, 100 billion data, right? So every partition is basically containing 10 billion records, which you are storing in the state store. So you can either increase the number of partitions, scale it out horizontally. So instead of 10 partitions, now I can do 100 partitions. I have 1 billion records, much lesser size in the state store. And I can have these many number of KStream instances running in parallel, having lesser requirement on the disk and the memory requirements. So these are all you can easily horizontally scale if you design your topic and partitions accordingly. So start always in your design from topic, number of partition, KStream, capacity planning, perform the capacity planning on those things and scale it out. And then jump into this fine tuning of the rest of the stuff to improve the throughput and performance on layer by layer. So these are some of the example metrics, JMX metrics, which gets exposed. The most important part when you dig deeper into RocksDB JMX metrics, not all metrics are enabled by default. Only the info level metrics are enabled by default. So all your mem table sizes, block cache size. So these are our block cache hit ratio. You can easily see it with the info level. I would not recommend enabling debug unless you are running a test scenario in debug mode to do the performance fine-tuning of your overall streaming application. Then you enable debug mode and look at the additional JMX metrics, which can give you more insights on the RocksDB side. But by just focus on the info level on your production dashboards. And the most important ones are block cache size, block cache hit, miss, write stalls. These are some of the important JMX metrics which you should definitely take a look. Some of these are already there on Confluent documentation, or you can look it online and configure it accordingly. So finally, like, how do we configure these settings in RocksDB to optimize it, right? We can, to implement any of the RocksDB parameters, we have to first create a custom class, which implements RocksDB config setter interface. And there, like, you override the set config method. And there, like, in the options, which are the key value pairs for the configs, you can set the RocksDB parameters. Like I was mentioning about the mem table size, you can increase the mem table size by increasing the write buffer size. You can change the compaction style, level versus universal, or like the block cache sizes. So all of these different parameters you can easily configure by implementing this custom class, and then use that class when you have your stream app to put that RocksDB config setter class config. So on the second box, you see that where you are implementing the custom class instance. So this is how, like, you will set the configurations for RocksDB, have the new parameters, and monitor the performance by running your perf tests in your pre-prod or QA environment to look at the dashboards, whether it's improving your overall throughput and performance. And most importantly, look at the overall memory utilization and the CPU utilization, and fine-tune these parameters accordingly. So this is it. We'll have like 10-15 minutes to go through any questions. I hope this was useful. Anybody, any question? If not, then we can end this call earlier. Deepen, all good?
Yes. I guess I'm good. Just one quick question. So Flink. So when you
Mhm.
say Flink, it's a framework that includes this Rogs DB, mem table, and everything integrated with it. We just need to provide a code that would just format and parse the data as we need,
That's correct.
correct?
Yeah, so you'll implement the code and then you will do the job submit. So if you have worked on Spark also has a cluster, right? So you build your job, you submit to the Spark cluster, and Spark cluster has a resource manager, job manager, same thing like Flink has a job manager. So all of these Hadoop frameworks, they have the commonality that they are managing their clusters. You scale the cluster, and the cluster, you submit your streaming or batch jobs. So Flink, the good part with Flink is Flink provides both batch and streaming, uh, like
Mhm.
streaming frameworks or libraries or APIs, so that you can
Mhm.
easily write your data flows to perform batch or streaming operations. You submit your job, and Flink will then manage, job manager will manage launching this job to different task managers, and it will perform that operation. So
Okay.
your
And
deployment
what
part is
different?
taken care by the Flink, but in KStream, you have to manage your deployment. So in that case, like your app instances, you will take it up and CIC through CI/CD, and you will launch it on different, in like you will launch different instances. If you're running on Kubernetes, you will launch your service with these number of pods, and you will do the
Mhm.
deployment management aspect. But with Flink, you will submit it to the Flink cluster, and Flink job manager will deploy it accordingly.
S- okay. Got it. Thanks.
All right. Anything else?
Uh, can you hear me? Sorry. I guess there is some
Yeah,
network issues. There is delayed
yeah,
and
I can hear you.
okay. What different program language does this Flink support?
So Flink, you can use Java, you can use Scala, you can use Python also.
Right.
So it's again a framework, right? So you can
Mhm.
definitely configure those things. We'll have a separate session on Flink,
Mhm.
uh, uh, learning session where we'll talk about how to write a Flink application and submit it and manage it in the run a production Flink job.
Okay. Okay. Perfect. Thank you so much, Vijay. That's all I had.
Okay, sounds good. Thank you, Deepan. All right,
Yep. Thanks.
bye.
Bye.